Yeah, so the organizers first gave me 1 hour and then 45 minutes and then half an hour. So it's getting shorter and shorter. But then I'm expected to sort of fill these slots fully. So this is a bit of a challenge. So what I will do now is I have sort of an intermezzo. So before the break, I have been preaching active automata learning as sort of a nice topic. But now I want to describe you some example where we applied passive state machine learning. And so the context is again very similar. It's again one of these printers of OC, but now the application is quite different. In Holland, the funding agency for research, NWO, emphasizes that academics should collaborate with industry. And often that is quite a nuisance because you cannot work on the problems you really want to work on, but you have to work on the problems of today or tomorrow from industry. But then still, I do like this part of the Dutch research culture. And so there was a student of mine, he's just finished his thesis, Alexis Linard, and basically he was appointed on a project at OC with the main sort of topic like, okay, machine learning looks like a useful thing, so let's see whether we can do something with machine learning at OC. And in the end he had some nice results, and this results is actually used in practice, and it led to some nice theory. So those things do come out, and that's nice. Okay, so what is the problem? OC has these big printers, and they are shipped to different countries, companies here, companies there, printing offices, and different machines are used in entirely different ways. And so these days, of course, at the main headquarters of OC, they can monitor what goes on with all these machines, and they want to sort of optimize them. They want to set parameters in an optimal way. And so one thing they want to know are sort of patterns of printing behavior. So, for instance, you can imagine that a pattern AAAA, you just print n pages, one-sided, that's it. But maybe you have alternating pages which are treated in a different way. So then you have a pattern AB, 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 AB. Or maybe you have sort of little books which have a front cover, then a couple of pages, and a back cover. And so what people at OC asked us is, okay, can you automatically infer those patterns? Because then based on those patterns we can optimize working of the machine. Okay, so then we move to sort of automata theoretic mindset. So we have apparently a number of regular languages, but each pattern is a regular language, so we want to learn a union of regular languages. And we only have positive examples. We only have patterns that occur, but the printers, people are not going to tell us that they don't use certain patterns. So we only have positive examples. So Mark Gold already showed in 1967 that it's not possible to learn regular languages in the limit from positive examples. So what does it mean, learning in the limit? Well, suppose we have an enumeration of our language. So we have a long sequence, and all the words of the language occur in this sequence. It's an infinite sequence. Maybe there are some repetitions, but eventually you will see every word. Then a learner who wants to construct models, maybe after having seen 10 words, comes up with a model. But that model may be incorrect, and then a bit later he gets a counterexample and he has to refine his model. So we say that a language is learnable in the limit if eventually the learner will get the right model. And Mark E. Gold observed that regular languages cannot be learned in the limit. And that's very easy to see because suppose you have first see the word A, then you think, okay, this is a regular language consisting of the single word A. That's it. You give an automaton, but then you see also AA. It's a regular language, 2 words, A and AA, and you build an automaton, and that's it. And okay, this continues, and of course you will get new automata all the time, which are all incorrect because maybe the language is A star. So the task which Osei gave us is basically unsolvable. We cannot learn regular languages in the limit, let alone union of regular languages. Okay, but then Colin de la Higuera, our co-author, made some smart remark, and that's the only contribution he made to the paper, basically, but a really important one. He said you want to look at window languages. And that we did, and in fact those are learnable in the limit, and we can also learn unions of those languages. So that's what this part of the talk is about. Okay, so what is a window language? The intuition of a window language is that if you want to check whether any given word is in the language or not, you basically sort of can look at the string, and then using a window of size k, sort of go along this string and check every time whether the patterns you see are allowed, and if you only see patterns that are allowed, the word is in the language. So a window language is fully determined by a test vector. You describe which initial fragments of words are allowed, prefixes, so you have a finite set of sequences of length k minus 1. You have a set of allowed suffixes, sequences which may occur at the end of the word, and you have a set of sequences of length k which may occur at any point in the middle of the word. And then, because these are all sequences of length k minus 1 or more, we also have a set of short sequences that are allowed. Okay, so this fully specifies a window language. Let me give an example. So suppose this is our test vector. We say, okay, the word should begin with AB. It should end either with AB or with BA. And any segment of 3 symbols should be one of these possible sequences, ABA, ABB, BAB, and BBA. And then we also accept AB. So then, if we want to figure out whether a certain string, AB, 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 is in the language, well, how do we do it? We first establish that the initial fragment is in the language, right? AB is an allowed initial prefix. We check that the end of the sequence is okay, because AB is allowed as a possible end. And then we sort of move this window along the word, and we check at every point whether the segment we see in the window is actually allowed. So ABA is allowed, but also BAB is allowed. ABA is okay, BAB. Okay, yes, it's allowed, right? So that's how you can check it. You have a simple sort of way to check whether a word is in the language. So let's do another example. AB, AA, BA. Well, beginning is okay, the end is okay, first segment is okay. But there we have a segment BAA, A which is not in the language, and therefore this word is not in the language. Yeah, so this is a very elegant, simple concept of a window language. Window languages are parameterized by a window size, this K. So, of course, if you increase the window size, you can have more elaborate languages.
Could you explain again the English and our short strings? You never used it in your Automata, or did you?
No, yeah, so in this case, there may be a couple of strings with length less than k-1, which you want to have in the language. And so you just enumerate all of them. So here, yeah, it's just a very small print job, just 2 pages, that's it. But it should be allowed. Okay, so given a test vector, it determines a regular language, right? And we can describe that regular language by this expression. So all the short words are in the language. Then all the words that begin with an initial fragment and end with a final fragment are in the language, except those, here's a set minus, the words that at some point contain a sequence of length k that is not an allowed segment. So this is a simple regular expression describing exactly what are allowed window languages. So immediately we conclude that window languages, or they're also called KTSS languages, are testable in the strict sense, are regular. Okay, so given a test vector, we can compute a language. And so we have 2 sets. There is the set of test vectors. There is the set of languages, the subsets of sigma star. And given a test vector, we can compute a language. Conversely, from any language, we can also construct a test vector. Because how can we do it? Well, the short sequences are just all the short sequences that occur in the language. The initial fragments are just all the possible initial fragments that occur in words from the language, given language L. Same for the final language and same for the segment. So whenever, what is a segment? Any word v of length k such that there exist sequences u and v over sigma star such that u, v, w is in the language. V is a segment that occurs in the language. So we can go from test vectors to languages, and we can go from languages back to test vectors. Okay, so on languages we have an ordering relation. One language can be bigger than another language. It has a larger set. Similarly, on test vectors, we can also define an ordering relation. One test vector can be bigger than another one. So one test vector IFTC is less than I prime, F prime, T prime, C prime if I is contained in I prime, F is contained in F prime, T is contained in T prime, and component-wise I have inclusion. Wow, so then we have 2 partial orders, and we have functions from one to the other. That looks interesting. These functions preserve order. When one language L is contained in a language L prime, then the associated test vector of L will be included in the test vector of L prime, because if you can observe a segment here, you can certainly observe it there.
I guess you gave the instruction to define the test vector corresponding to language, but that construction is not unique. I come up with another test vector that produces the same language as well, right?
Mm,
For example, I could include I could just concatenate some of those patterns.
yeah, but I have these results, and then I will show that these are very useful. There were different constructions are possible, of course, yeah. Of course, for those who are familiar with this starts looking like a Galois connection. So we actually proved this is a Galois connection. So what does it mean? Well, for a Galois connection to exist, you need two partial orders. You need a function from one to the other and from the other to one. Both these functions should be order preserving. And then we have this sort of unique property that if we take a language and we compute its associated test vector, and that test vector is less than some other test vector z, and then the original language here will be below the language obtained by taking the language of this set. So this connection, and this is an if and only if. Galois connections were invented, as you may know, by the French mathematician Évariste Galois. There are even t-shirts available on the internet which you can order with the picture of Galois, but I'm not such a nerdy type, but I feel tempted to order a Galois t-shirt. He's really a great guy. As you know, he was a brilliant young mathematician, but then he got involved in some fight, and so there was a duel. And the night before the duel, he wrote down his ideas on mathematics, solving, I think, fourth order equations. But then I think he worked too long, so he got killed in the duel. But these documents, they are the basis for group theory, Galois theory. It's really an amazing document. So a Galois connection is a particular correspondence between two partially ordered sets. It's correspondence of the type I described. There's many applications in mathematics. People in category theory, they sort of generalize it, and then this is called adjoint functors. But also in computer science, Galois connections are used a lot. And they are particularly used in the theory of abstract interpretation. And when you have a program, you sort of want to abstract from it, and rather than, say, have integers, you want to abstract to 3 values or 2 values, and then analyze the abstract model and transfer results back to the original program. So this is what is going on in abstract interpretation. And the same concept of Galois connection is useful in learning. So now comes the fun part. So these window languages were not new. People studied them before. And there are a couple of papers of people who actually studied learning algorithms for window languages. And they prove lots of results. But all these results are just corollaries because we have a Galois connection. Because as soon as you have a Galois connection, there are quite a number of simple basic facts which automatically follow. They hold for any Galois connection. So, for instance, several people observed that if you compose these two functions, so you take a test vector, compute a language, and then go back to a test vector, you get, then you have a function, or you can go from a language to a test vector and back. And both these functions are monotone and idempotent. If you apply them twice, you get the same thing. Then, if you take a test vector and you compute the language, and then you compute a test vector for this, you get something which is less than the original test vector. The point here may be that this original test vector may contain certain junk segments, segments which are allowed, but which can never occur in sort of a real world. And then the other inclusion is if you take a language, compute a test vector, and then bake the language again, you get something which is bigger than the original language. Then another theorem which says that if L is less than language of some test vector, then in fact if we take the gamma, taking the test vector and then the language again gives you something which is less. Okay, yet another lemma. There are all these lemmas which are proved in the standard textbook on Galois connections and which were proved earlier, often using long proofs in the literature. Okay, so using all these lemmas, Garcia and Vidal proved in 1990 that any k-testable language can be identified in the limit from positive examples. And the intuition for this is very simple because basically window languages are defined by the segments you can observe, the initial segments, the final segments, the segments in between and the short sequences. And if you have an enumeration of the whole language, at some point you've seen all the segments. And therefore, from that moment on, your language will be fixed and you've learned it. You've learned it in the limit. Yes? So if here in this setting you assume the learner knows K. Of course, in our OC case study, we had no clue what K was, but then we first tried a small k, and then we got unreasonable patterns, and we continued until we got nice patterns. Okay, now we want to move to unions of these languages, because we don't want to learn a single k-testable language. We want to learn sort of a union of simple patterns. So, given two test vectors, of course, you can take their union. Basically, you take the union of the initial fragments, final fragments, segments, and then you have to be a bit careful with the short sequences. That is sort of a technical detail. But basically, you take the union. And similarly, you can take the symmetric difference of two test vectors. So, window languages, and this was also known, are not closed under union. So regular languages are closed under union, but window languages are not. So here's an example. Here I give two test vectors, z and z prime. Z corresponds to this language. It has all the words that begin with AA, end with AA, and in between you have 3A, so this is very A-like language. It looks like this. And then the other language is a bit more complicated. It begins with BA or BB, but it should end with BB. And the short segments are BB. It should end with either AB or BB. Okay, that corresponds to this automaton. Now, if we take the union of these two test vectors, we get a... you would expect... let's see if... Yeah. You would expect that you get the union of these two regular languages. So then you can describe that by an automaton which either takes the A part or it takes the B part. However, the language the word AAB is accepted if you take the union of these two test vectors. Why? Well, AA is allowed as an initial segment. AB is allowed as a final segment, according to the other one. And AAB is allowed as a segment, according to Z prime. But that's not allowed in this language. Because here, either you begin with an A and end with an A, or you begin with a B and end with a B. It's not allowed to have this crossover where you begin with an A and end with a B. So window languages are not closed under.
Your counterexample does not show that window languages are not closed under union. It just shows that this union construction is not the right one for the union to window languages. In order to show that they are not closed under union, you should show that there is no window language that accepts the union,
right? I don't do all the details of the proof, but that is actually the case here. So if you take this regular language and you compute the test vector, then actually you will get the union of these two. Because AAB is an allowed segment. It may occur at the end here. And AA is an allowed initial fragment, and AB is an allowed final fragment. So if you take this regular language and you compute a test vector, you get this thing. And then if you compute the language for that test vector, you get the smallest k-testable language, which contains these segments, and you get this one. So they're not closed on the union.
I guess the number k will be different. So this is a
No, but we fixed the k. Yeah. I think this goes wrong. No, this one doesn't go wrong. But there are other examples which go wrong for different cases. Okay, so using our Galois connection, we can easily prove that any language that is a union of k-testable languages, so that language itself doesn't have to be k-testable, but it's a union of k-testable languages, is identifiable in the limits from positive examples. But then the question is, okay, how do we compute the patterns? And so here we sort of use a clustering approach. So basically what we do is, given a word, we can compute a test vector. We can just look at all the segments that occur in this word. Now sometimes we can take a union of two test vectors, and then we get the union of the languages. Sometimes we can take a union. But which union should we take? In which order? So we define a clustering approach as follows. So the size of a test vector basically is the number of segments that occurs in it. And then the distance between two test vectors is just the size of the symmetric difference. How much does it take you to go from one test vector to the other? And we can prove that this is a metric on a set of k test vectors, and that allows us to use clustering. So basically what do? For every word that comes in, every pattern of print jobs that is registered by OC, we compute a test vector. We compute the distance matrix. We compute what the distance is between these vectors. And then we just try to merge the nearest pair of test vectors as long as this is allowed. The language of the union is equal to the union of the languages. We update the distance matrix, and yeah, that's it. So we applied this to the OC case study, and for IP reasons, I cannot show you the sort of real examples, but you can imagine it looks like something like this, that we have one pattern just A's, that's a homogeneous print job. Then AB, 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 etc. That's another pattern, heterogeneous. And then there is this cover thing. Now let's see, then we have, the pattern A, B, C plus A. That's sort of a booklet. So we were able to identify these patterns, and the fun thing is that this is actually used. So printers of OC are now being configured using this algorithm. So when a new printer occurs, they figure out what the patterns are, and based on that, they configure the machine. Okay, I think I would like to stop here. There's still a bit of time left, but this is sort of a natural break. So my message is that I think, what I very much like about this paper is that on the one hand, there is this theory, there's just a result about Galois connections, and then on the other hand, there is a company which uses it. And a few times in my career, was so lucky to have such results. It's rare, of course. Often industrial problems are really ugly, and nice theoretical results are not useful at all. But sometimes
the intersection
there
is not
is
empty.
A marriage. Yeah.
Good. It's good to know that the intersection is not empty. Are there any questions? Yes, please.
How we can understand if we should use this approach or not? I mean, in compared to the Avastar or K-testable, what is the type of the applications that I should this approach?
Yeah, well, the key thing is that you want to learn a union of regular languages, right? Mm-hmm. So if you just want to learn one regular language, you can use either L-star or some passive learning algorithm off the shelf. But this is a different situation. Here we want to group words into classes and sort of come up with union. I'm not aware of other learning algorithms for learning unions like this. So.
We still have time for a couple of questions, if there are any.
My question is, how did this collaboration with OC was made? Was it started from a proposal from you, or they didn't know about the application of these kinds of automata in their printers?
So we have a long-standing collaboration with OC already for 15 years or so in different projects. So at some point, one of the projects ended, and we were just chatting with the OC people about what possibilities could be for a successor project. And then you have a brainstorm-like meeting. And so then, of course, they raised this issue of machine learning. They said that we have so much data of our printers because we log what they do, and these data are just sitting there, and we want to use them. We want to extract useful information. So this is one example, but my student did a couple of other examples where actually he showed he can extract useful information from data, which for data scientists is no surprise, of course. There are many things which you can do. And then the fun thing is that when it comes to concrete case studies, there's always sort of a bit of negotiation. So from the OC side, they say you could work on this or on this or on this. And then, I'm sort of an automata theory person. So when an example like this passes by, then I think, okay, let's do it. But actually, we also did Has some examples where we used Bayesian learning and deep learning. Of course, you can use those as well.
Okay, any other questions before we go for coffee or tea? Thank you.